Welcome to this class on Exam 1 review for CSE 574, Recent Advances in Wireless and Mobile Networking. So this exam will cover the first 6 modules, and you guys have reviewed the videos and the reading list, etc., and asked the questions. There are lots of questions, so I'm going to move fast. And so the first question on this module 1 is on slide 26. So we go to slide 26. Okay, the new questions are, clearly marked differently. So is the calculator mandatory? And the answer is no, it is not mandatory. You can do the mental computation, and many of us can do mental computation. And in the worst case, if you leave the computation incomplete, only a small number of points will be deducted for that. But basically, half of the points are for the method, other half are for the final answer. And if you didn't get to the final, but you're on the right track, it is not a problem. But it would still help if you bring a calculator. You cannot use your iPhone calculator, and you cannot use any calculator with any kind of memory. The TI-30 is the one, and actually any simple calculator will do. It's not much math, but basically, you do have to do DB calculations, etc., etc. So that kind of thing, okay? Second question, what topics will be covered in the exam? And let me start the chat, and let me start the transcript. Okay. All right, so if there are any additional questions, please ask in the chat box. What topics will be covered in the exam and what is not included? Module 1 to 6 are covered. All topics discussed are included, okay? So you cannot say, well, this and that, right? The answer maybe in the slides or reading list. Okay, topics not included in the slides are not included. Basically, so if we talk about Wi-Fi and we talk about something that we didn't put in the slide, nothing. But the thing is, if it is in the slide, you need to get more details from the reading list, and I can ask more details from the reading list. Okay, so I assume that you have read the reading list and you have read the slides. That's all. Will the exam use acronyms? And the question is in capital YES. Yes. We are not going to put the, what is OFDMA in a full form, or TDMA, or TDM, or TDD. These are acronyms will be flying left and right, okay? And you have to know them by now. Okay, so those acronyms have to be known. Next. Can we use both sides of a piece of paper, handwritten or printed? Yes, both sides, handwritten or printed. It doesn't matter. And it can be printed in any size font. There is no font limit. You can print it as long as you can read it. Can I bring a basic calculator? Yeah, basic. I don't know what basic means, but basic is something which is TI-30 or equivalent. TI-30 is simple calculator. Basically, it is any scientific calculator that you have seen or is on your computer, but you cannot use your computer, right? How much time do we have to finish the exam? The exam is 50 minutes, 50. And it starts exactly at 1 and finishes at 1:50, 1:50. Is this location confirmed? Green Hall L0120? The answer is yes. Okay. And Zibo, can you tell me a little bit more about which side of the staircase is this room is? What do you do to get there?
It's in Green Hall and it's in the basement. So if you enter from the eastmost door on the Green Hall building, you can just go inside the building and go downstairs. Then
is it just next to the stairs, or you have to walk a bit from the stairs?
Yeah, you have to walk on the stairs. Downstairs. Okay. It's in the basement. Yeah.
All right. So somehow you'll find it. I will be there tomorrow, and we will all find each other.
Yeah.
Let's see. Yeah, the next set of questions is it possible to have an extra TA session the day before the exam? And Jibo, can we have a session tomorrow?
Yes.
What time is your convenient for you? Basically, you have something else on classes on tomorrow?
After 11:30. you'll
Okay,
be
so
fine.
don't
Yeah.
keep it 11:30. Just keep it in the afternoon, late afternoon, so that people have a question, they can still come to you. If they have a
Okay.
question after your TA exam, then they will again want another TA hour.
Yeah, how about 4 to 5?
4 to 5. Okay,
Yeah.
so tomorrow, Tuesday, 4 to 5.
Yeah.
Okay, and please put a
Yeah,
the session on the canvas so people know where to go.
okay.
Right?
Upgrade on canvas. Yeah.
Okay. All right. Next. Do we need to remember all the numbers and percentages in the reading list? Not really. I mean, but the thing is, I mean, I don't expect you to read all the numbers, but some key numbers, like what rate is IEEE 802.11b? If you forget that, and then you're an 11a or, things like that. So those are some numbers that are very round numbers. They're not, 2.35679, but, those numbers are very common knowledge. Okay. And they will stay. I mean, they stay in my memory for 50 years and they must stay in your memory for at least a day. But, the thing is, I won't remember the year of any standards. I mean, like I know 802.1Q. I participated a lot, but what year it is in, I don't know now. Okay. And so the years are not important. And some of the numbers which are very minor, how many carriers they use. I mean, if you don't remember, that's fine. But the thing that they operate in 5 gigahertz, you have to remember that. Okay. And whether they're 2.5 or 5 or 6 or 7 or 8 or 60, those are, some general statistics. In general, when it trends, not exact value, and you have to remember the trends. So, for example, if somebody asks you what is most of the traffic right now on the wireless, you should know that. Okay, I mean, you may not know exactly how many megabytes, and I don't know how many gigabytes or terabytes that is, but we know that out of all the things that we have, whether it is audio, video, sound, or whatever it is, like data, what is going on the net. Page down. Okay. Will we have all of our homework returned before the exam so that we can use it as a review for the material as well? Zivo, what is the status?
Up to homework 5, all are graded, but homework 4 and 5 haven't posted the grades yet. So should I post them? I mean,
yeah, you should post all the grades. I mean, nobody can submit anything. Just change it until deadline to 26th or 27th. Okay.
Okay. Yeah.
And post all of the homework, including homework 6.
Okay.
Okay.
I will post them all. Yeah, today.
Yeah. Homework 6, and so that in tomorrow's session they can still come to your session and clarify if they have some issue with that.
Yeah, no problem.
Okay, and change the date. I mean, I might be able to change the date too from my side, if I remember it, right? But change the until date. Otherwise, somebody will see the answer of person X, and then they will go and submit for person Y. And some of the dates are still within 10 days. So now there won't be, basically everything is now worth 0 after this one, right? So there's no late penalty issue after this. You get 0 marks.
Yeah, for homework 6, we have this issue, but I will close submission.
Yeah,
everybody agrees.
Some of the homeworks will be disclosed today. That's another thing is, I think the homeworks are closed now at 1 p.m. Okay, they are closed. Some of the solutions will be shown just now. So if you haven't submitted the homework, they're done, basically, because I cannot show the homework solution and still accept your answers. Okay, so the homeworks are closed right now. Even if the Canvas takes them, we will not take them. All right, that's module 1. Let's move on to next module 2. Module 2. So questions on 4, 9, 16, and 21. And there are lots of questions this time, so I'm moving a little bit faster than usual. 4. Is this included in the exam? The history. The question is history included in the exam? Yes. Years are not important. You don't have to remember that the Hertz discovered in 1980 or 1880, but you have to discover that why Hertz is famous for. Okay. And then, for example, wavelength, these are things that are, key parts of the history of the wireless. And so those years are not important, but the rest of this, some of the data points, whatever it says here is important. Okay. Next, 6. Was it 6? I might have missed. Okay, so here it is, 9B, 9. Is there any device that could be both IoT but not M2M? Okay, so digital devices controlled by internet are all IoT. So you can control by the internet, they're all IoT, Internet of Things. Okay, easy modern thermostats. Okay, there are a lot of things in the home that you can do by your iPhone. That means you're going through the internet. Okay, and M2M is the subset that serves another machine and you don't even see it. Okay, M2M is the subset that serves another machine, e.g. industrial controllers. Okay, so the industrial controller might be connected to their controller or industrial, let's say grinding motor or something, maybe connected to a controller by internet, not by wire, by internet. Okay, some form of internet, right? Then it is also IoT, but it is M2M, and human beings are not involved in that loop. Human beings are probably using the server, and the server is using their server, their sensors. Okay, and so easy industrial controller. So there are two examples. What is IoT and what is M2M? M2M is a subset of IoT. IoT, anything that is connected to the internet is IoT, but some of them are also controlled by a machine. And that becomes M2M. All right. Next. Okay, I think I might have missed something, so I'm going to go back to the first one. 4, 9B, 16, and 21. Let's see, 16 and 21. What did we do on 16? Do we need to remember details in this slide? So this is about these new technologies. Yes, when they're covered in detail later. So right now you don't have to, okay? But if we cover them in later modules, you have to. Now, I don't know if anybody of remember AX, okay? Anybody remembers AX? It was covered in module 6, and this is called Wi-Fi 6. All right, if you don't remember, then you really need to do some more reading today. Okay, because we did cover it and we mentioned that the name AX. Similarly, AD, all of these have been covered actually. Bluetooth has not been covered, LPWA has not been covered, and that's all. So I mean, like, the thing is, you don't have to remember all these names because we didn't cover them, but if we cover them, then they are in part of that module, if not part of this module. Okay, 16, it was 20 after that, 20, and the numbers are gone now. So what happened to 20? Maybe this was 20. Yeah, right here. This is already covered 21. All right, I think we are done with this module. We go to 3. There are lots of questions on number 6, by the way. So that's why even if we finish 2 modules, we might still be kind of running a little bit late. But 3. 8, 9, 10, 14, and 25. So we go to 8. Okay. Electromagnetic spectrum. Is this included in the exam? This is included in the exam for sure. This is one of the key things you have learned in this course. Okay. Now, you don't have to remember that, okay, Wi-Fi goes from, blah, blah, blah to blah, blah, blah. Our radio goes at this. No. But the thing is, you have to have a general knowledge of, that, where things are, low frequency, high frequency, microwave, medium, high frequency. I mean, I'm not going to worry about the numbers, but I really need to know some relative idea of where things are. That visible light is different than optical fiber communication. There are a lot of things that we discussed here. Okay. And those things you have to know by now. Now for the exam 1, and at the end, and after exam 1, you can forget it again. But I hope not. Okay, these are some of the key things that we learned. This is a very key slide. You don't have to remember exact ranges. I wouldn't ask, okay, so how long is the wavelength? How long is the whatever this range is, okay, or this range is here. But we don't use visible light so far generally. Generally, let me put it this way, there's an exception to every statement. As soon as we say that, there are people who say, well, there is a light fi. So the thing is, we generally use these 3 bands, but you don't have to remember these 3 bands. You just have to know that there are infrared radiation. It is infrared, which is used in optical communication, and microwave, which is used in, Wi-Fi. All right, next. 10. dBs are related to watts. How does it relate to wavelength, amplitude, frequency, etc.? Okay, if the voltage is constant, you can calculate the watts from the formula P is equal to V square I. Okay, now this is all physics, by the way. We didn't teach it in this class, but I'm just telling you that in the physics in high school, they teach you how to calculate power from voltage and current. Okay, and so V square I is power. And if now the voltage is not constant, generally the voltage could be like this, a square wave or a sine wave. If it is a square wave, then it is constant. You just calculate V square I, and you get the power, which happens to be constant because the square of the V is constant. In this example, left example. In the right example, it is not constant, and therefore you have to do the square of VI and then an integration. And that's why now all that integration is taught in some class, lower grade class. I'm not going to go through that. Wherever they teach integration, they teach you, but we use RMS, root mean squared value. Okay, root mean squared value is what you square and then multiply by I. So this thing has a root mean squared value, which is if the amplitude is A, then A upon square root 2 is the root mean squared value. I wouldn't ask you all this detail, but somebody asked the question, so I have to clarify it. Okay, because I'm just going to deal with this kind of a stuff, but somebody asked, how do you get it from frequency and amplitude? So the frequency doesn't really matter if it is sine wave, because it is 50-50 up and down, and then you square it, everything becomes positive, and then you do RMS, you can square that and multiply by the current. The amplitude indicates the voltage. So whenever we say amplitude, we really mean the voltage. Okay, it could be, so the thing is, we generally use power. And we have shown you power in some of the graphs. For example, in OFDMA, we showed you half sine waves. Those are power curves. They are not sine waves, they are square of sine waves. Okay, and they were obtained just by squaring because we want to get the square of the whatever, right? Sine wave. But sine wave is the voltage. Now that's a detail that we didn't cover here, and I really don't know whether that is important, but somebody asked as to how do you calculate power, so I put it here. All right, next. What is the exact range of a bit and a pulse in this figure? All right, a pulse generally is, which is either defined by, pulse is generally a constant signal. Now, constant is a word which I should have put in the quotes, because this is constant. And this is constant. So these are the pulses. Okay. But if it is a sine wave, as long as everything is constant, the amplitude is constant, the frequency is constant, that could be a pulse. Okay. Now the question is, what is a bit? Now the bit is defined by the coder, the coding person, or the coding defined for it. So here I defined that my 1 bit is a long pulse followed by a short pulse. Here I said any pulse up or down is a bit. Here I said that it is not a pulse, it's a transition. It's a bit. So it can be defined by 1 or more pulses or a transition. Okay, so the bit is up to the person who is signaling, and the pulses are in the signal. And there could be variable length, there could be constant length, there could be sine wave, there could be anything. Okay, if there are any questions, please ask in the chat box. And we move on to the next. Okay. Is there any work being done for ternary instead of binary? The powers of 2 are easy. So this is a binary, and this is a basically quad 4 levels. And then we have 8 levels, and then we have 16 levels. Now, why we don't have 15 levels? Well, 16 is good enough. Okay, powers of 2 are very easy to do. And so we jump from 8 to 15 and not to 10, 11, or any number of levels. Okay, similarly, we jump from 2 to 4, not to 3. Now, you could find out a method where it is very, very easy to do this in hardware, software, or whatever, and then you could do that. But right now, people are just staying with powers of 2. And you saw that QAM had 4 levels. QAM had basically 4 quadrature amplitude modulation. Maybe QAM didn't have, but basically after QAM, because there in the QAM, actually, I just have to correct myself. In QAM, we have 4 possibilities which are not amplitude, okay, because there are 4 phases. But as we go into the higher levels of QAM, we can have multiple amplitude and multiple phases, but they're all powers of 2s. All right, powers of 2s are easy. Next. Why is TDD more flexible for sharing downlink to uplink data rate? And the reason is it is easy to dynamically change the time allocation for DL versus UL compared to frequency allocation. So if I give 90% of the frequency for downlink and 10% for the uplink, then 90 to 10 ratio is fixed. If I want to change that, I will have to probably change the antenna, okay, which is very difficult. And if I want to change the time, I am transmitting 90% of the time downwards and 10% of the time upward. It is very easy for me to make that 80-20 or 70-30. Just on the whim, because there is high traffic in the morning, I can just keep one ratio in the morning, one ratio at 11 o'clock, one ratio at 12 o'clock. So the time is much easier to control, and therefore time division multiplexing is more flexible. Okay, duplexing, time division duplexing here. No, not multiplexing, duplex, right? All right. Then this is what, 25. All right, I think we are done. Oh, actually, I didn't make it high. Okay, let's just see. So 25, there is 1 on 25, 21 and 25. Maybe that was it. So let's go to 25. Yeah, why is TDD? Okay, that was 25. Okay. All right. Then we go to 4. All right. The questions are 10, 12, 26, 29. There are lots of questions. So let's go to 10. The number of questions increase as we go deeper into the topic, right? So now let me make it bigger and go to slide 10. I missed slide 10. Right here. Okay, the question is, why having a large symbol duration means having less? Okay, I should have said more. I thought more. Okay, having less ISI. When did I say that? Symbols become wider, they limit the number of bits. So, okay, all right. Fatter symbols need more intersymbol gaps to avoid interference. So, to avoid interference, you need gaps. So basically what happens is whenever you send a symbol, which could be just impulse, you need a gap between them. And the gap has to be proportional to the to the width of the symbol. So you say, okay, all right, I will keep 80% for the symbol and 20% for the gap. As long as you keep that ratio 80-20 or something like that, or 8-75-25 or whatever number, depending upon your electronics, you could go to 90-10. But basically, you have to keep some gap between the symbols. All right. And as the symbols move, they become fatter and fatter, and the fatter symbol will become more fatter. Okay. So if the gap is not sufficient, then they will run into each other and there will be ISI. That's the idea here, that your gap has to be more. By more, I mean the absolute value. If you do by ratios, that the gap is 25%, 1/4 is the gap and 3/4 is the symbol. Then it doesn't matter what is the symbol width, because as your symbol width increases, the gap also increases 1/4 and 3/4.
Professor,
Okay. Yeah.
that's for slide 25. That's you said there, and there is also another thing.
Okay, let me see the slide 25. So let me read this slide because I wasn't sure where this one. A large number of carriers, a smaller data rate, larger symbol duration, less inter-symbol interference. So this actually is smaller data. This is the thing you are questioning, right? Yeah.
There is another part that I missed. We have a similar point in slide 38 of module 6. 38 of module 6. These two.
Okay, I won't go to module 6 yet. So let's just continue on this one.
Okay.
Okay. So large number of carriers will mean that it's larger symbol duration. Okay. And here, larger symbol duration is just assuming, by the way, that we have proportional gap too. Okay, that was assumption. The thing is, inter-symbol interference happens for two reasons. One is that everybody gets fatter as they go through this tunnel. And the question is, how much is the gap? If two people just go on a very wide road, they can go miles long, right? On the other hand, if those people go on a thin road, they will not be able to go too far. So the gap is important, which was not mentioned here. Larger symbol duration and, and the gap, we didn't say anything. So this is in that sense, the less symbol interference, I will have to correct that statement because the inter-symbol interference depends upon the symbol duration and the gap. Now there is one more thing. Let me correct this one more also. So what we do is when we have some part of the symbol which is called prefix. Prefix. And that generally increases in proportion. Okay. And so that actually becomes part of the gap. What it does is that we take some part of the last and put it in the front or something so that this is redundant information. We put it. If you get it, good. If you don't get it, it's last, no big deal. So the gap is there, right? And that gap is what makes it okay because now you can have a lot more gap with the larger symbol. Okay. So the ratio is considered fixed here. And the ratio of the gap to the real thing, and the gap includes the prefix. All right, now, let me go back to the slide I was in. Was it here? 10, yeah. I put it here because it was very clear from here. And I'm sure you put 25 there, but then I moved it to here. Next, now I lost track, so I have to go back to get 10. After 10, we go to 12 and 26. So let's go to 12. How to correctly use d minus t raised to minus 4 law. Whenever you want to determine the height of the tower and its reach, you use the PR formula. This is per power received. See homework 4, and we use it in the homework 4. Basically, what happens is that you really don't use so much of a formula. You do the measurement. So the phone company goes out and does the measurement at various points in the city, various points in the terrain, in the mountain, on the highway, and they figure out where they get enough power for your cell phone to work. All right. And if they don't go to some place, they can approximate it by this formula. Okay. And a lot of such surveys have been combined and they published. And so the number varies from 1.5 to 5.5. Okay. So this is what is done. Also to determine the tower height, I mean, if you need to put for a very large distance, then you put the tower height, HT should be large, then it can go to large D. HR, receiver height is fixed. Receivers are all on the ground, maybe 5 feet of the ground. The only thing you can control is HT, height of the tower. And D, the distance you want to cover with it. Because then there will be next tower that will cover you. Okay. All right. Then okay, here. Can we say OFDM uses time division multi-TDMA and OFDMA, whereas TDMA uses FDMA plus TDMA? The answer is all wrong. Okay, so let me explain this thing. OFDM, orthogonal subcarriers. Okay, when you say FDM, frequency division is there, but it is not multiplexed. So there's no access. The access is only by time. But the thing is, the frequency is divided orthogonally. What that means is that you have subcarriers. It is not one carrier. Okay, when you are given a band, let's say, 2.4 gigahertz, you could use the whole band in one piece. All right. And if you use the whole band, that will be a one carrier, single carrier system that will be very inefficient. On the other hand, you divide that into pieces and use this whole band again, but into pieces. That is multi-carrier system. That is very efficient. So OFDM is the new thing with the OFDM was that realization that you should divide. So there is FDM here. Frequency division, multiplex, frequency division, right? So just to be clarifying that, what is this thing for? So this is, so I put the word subcarriers, orthogonal, and they have to be orthogonal. So this is different from FDM, which was there before, that these carriers are orthogonal. So these have been placed with such power and format that they are orthogonal. They don't interfere. If we use orthogonal carriers, and use thousands of them, then you have OFDM, and you can divide by time for different users. That is OFDM, right? On the other hand, you divide both by time and frequency. You give 5 subcarriers here to this guy, 10 for this and 20 for that, and 10 for this and 20 for that. You divide on both time and frequency. That is OFDMA. Okay, so the OFDMA is always shown in 2 dimensions as a frame, just like this as shown here. And in our papers and in our contributions to the standards bodies, you will find lots of such diagrams. Because this is one of the important research problems for computer scientists to figure out the allocation. When you want to have optimal allocation, and this guy needs this much, and that guy needs that much, and that guy needs so much, all the requests are given, then you have to allocate. And this is done on a frame-by-frame basis. On every frame, the tower tells every user that you can use these 5 frequencies for this particular time. And the other users will use the other time and other frequencies. All right, that is OFDMA. So OFDMA is orthogonal subcarrier with FDMA and TDMA. Now, TDMA is not FDMA plus TDMA. OFDMA is FDMA plus TDMA. So I think you probably, in a hurry, forgot to put here OFDMA. Because there's no TDMA in this slide. There's a TDMA here, but it says whatever. So OFDMA uses TDMA and FDMA, but the key thing is that the subcarriers are orthogonal, multiple subcarriers and orthogonal. If we just put FD, then that means frequency division of the bands into the subcarriers, right? Frequency division. And if you say FDMA, then you divide the subcarriers, you divide the pieces, right? Or you divide at least the band. So anyway, so you have to distinguish between the band and the carriers. There are so many carriers here in this band, and then we are allowing people to access a particular piece of it. All right, 26, there is one here. 19.4 kilohertz with 128 FFD was used in mobile WiMAX for 1.25 megahertz. He's just restating this one. Oh, this was he's restating the question here. That 19 was used in 1.25 mega. Okay. How is that possible? Well, if you divide 1.25 megahertz by 10.94 kilohertz, you get 114.26. All right, so these many subcarriers you need. Of course, you cannot have 0.26 subcarriers, right? And that is your question, and that is a valid question. No. What you do is just use 114 subcarriers, integer number of subcarriers, right? But your FFT has to be power of 2. So the next power of 2 above 114 is 128. So we will use 128 FFT. All right. I think, and whoever asked this question, they multiplied 1094 by 128 and said we get a lot more than 125. Yeah, you will get more than 1.25, but we are not using that. We are using just 114 of those. Okay. But FFT doesn't work for 114 unless you go by power of 2. Okay, so all the FFTs are power of 2s, and some of the rows will be zeros, and that's fine. FFT works. All right, that's the question. I think now let me just go back to the home and see where we are. 27, 29. So let's go to 27, 29, 31. 27. We finished that. 29. Why does mobility require below 10 gigahertz? Mobility requires below 10 gigahertz. Doppler spread. Okay. Now, the Doppler formula is VF upon C. If high frequency, there is a larger shift. High frequency. Right? And if you're going very high speed, this is your velocity. If you're going at a very high speed, then you need even a smaller frequency. All right. And can you please go over the solution to homework 4? Okay. All right, I will. So I don't know whether these two questions were in the exam or they were on Piazza. I just added them whenever I saw something asked on Piazza. I try to put them here so that the next year questions, the student will not ask the same thing. And I have actually corrected this homework so that a lot of people ask, how do you do using dB? Well, the idea was you do it in log scale. And this was said in the Piazza that you use log scale. But you know, if people still question, and the question came up again, even in this, I think said there was same thing. How do you do it in dB? All right. So you use dB and dBm, but not watts and whatever it is, right? I mean, that's what my answer was, that you just use log scale. But anyway, let me show you the solution. Now, before I show you the solution, I want to reiterate that this homework is now closed. You will not be able to submit any answers. And so I will go there. Let's see. Let me wait on that one until we come to the end anyway. Let me see here, this one. Homework 4, again, questions part A. What does it mean to do all calculations in dB? So I said, use a log scale only, add, do not multiply. I think this was the answer I gave on Piazza, whoever asked. And I put it here. And then this time, because somebody asked the question, I Googled it, and it said that dB and dBm cannot be converted to each other. dB is just a ratio, and dBm can be converted to watts and referred to power. Is this correct? If so, how can dB be used in calculation of signal to noise ratio? How can dB be directly used to calculate this solution? Okay. So this question has been asked so many times. I just put it word by word. Generally, I shorten the question so that we just get the meat of the question, but this is word for word, okay? So my point was exactly the same, that when I say use dBs, was that use a log scale only. You do not add. If you use anything in watts, you have to add. But if you use dBm, it's okay. dBm is not dB, but dBm is in log scale. And so that is just a general way of saying in the wireless world, okay, so we are going to do the calculations in dB, and you never really used anything in non-dB, by the way. So in wireless world, we say, okay, I'm sending you 25 dBm, how much you are getting? I'm getting 5 dBm, so the loss is so many dB. So you take 1 dBm, you take other dBm, you subtract them, and you get the dB. Okay, dBm minus dBm is dB. You get that? So an example is actually this, maybe this thing itself is an example, this when we go to the solution. But if I send you 1 watt, 1 watt is 1000 dB, right? And if you get 1 milliwatt, that is 0 dB. Okay, sorry. 1 watt is 1000 dBm, 1000 milliwatt. 1000 dBm, M is for milliwatt, right? And you get 1 milliwatt, that is equal to 0 dBm. 0 dBm is 1 milliwatt, right? So you subtract, so how much is the loss? 1000 dB. Now you can do it in the watts. You take 1 watt divided by 1000 watts, 1 milliwatt, you will get 1000. Take the log of that, whatever, and then multiply by 10. So you will get the similar things in by doing division, but I don't want you to do division. I want you to do in dBs. Okay, so dBm minus dBm is dB. Actually, I should add that because people keep asking me, how do dB cannot be converted to dB? Well, dB can be subtracted, dBm can be subtracted by dBm and it becomes dB. Subtraction is division. Okay, you get that? When you subtract in the log scale, that is a division. And therefore, if you take a dBm and subtract dBm, the answer is not in dBm. dBm minus dBm is dB. Anybody has any question, confusion about that?
Professor, when we add dB plus dBm,
Yeah,
what's
that
the
becomes
unit?
dBm.
Okay.
You see, that's exactly the point. When you multiply dBm by whatever number, that is like adding dBm to dB, and that will still remain dBm. Okay, so that's a good one. I should put that math here so that there's no question that dBm minus dBm is dB, and if you take one thing on the other side, dBm on the other side will become dBm is equal to dBm plus dB. All right. And so basically, the idea was that you have to start thinking in terms of dB. No wireless engineer will think about absolute values. They don't do any calculations on absolute value in any paper. Okay. They think in the log scale. All right, next. I think that's probably the end, but let me just go back to the home again. Let's see, home slide. 31A, 31B, I think we finished that, 29 we finished. We finished all of these, so we go to 5. And 11, 12, 13, 14, 16, 19. So this is pretty continuous. We'll go to slide 11. Okay, so here's the question. Does the time duration in RTS include retransmission time? So here I'm ready to send. So when you say ready to send, you have to tell that I'm ready to send for 1 hour, right? At that time, that does not include retransmission because you don't know whether you will need a retransmission. That is a reservation you want, right? I mean, when you book a flight, you don't book for the second flight simply because, hoping that you will not get the first flight. You might, if you have a lot of money, you might. But the thing is, these things cannot be reused, so they are non-refundable, right? In some sense. So you just can't, buy 2 tickets. So what you do is you just say, I want so much. If you want to retransmit, then you have to start from the beginning. You have to send another RTS, CTS, and then send. Okay? If any of these 4 messages don't make it, you start from the beginning again. So there is no retransmission considered while starting. Will the data remain in the buffer until winning the next access? All right. So the question is, suppose you didn't win. You said, I want to send, and you didn't win. Or you had there are other cases where the data will not make it. You will not get the acknowledgement. Will the data remain in the buffer? Yes. The transmitter will keep it in the buffer and will retry again. If it doesn't get the ACK, it did the 3 steps, but it didn't get the ACK. It has to start again. Okay. So how long will it do that? Well, then there's upper limit. That will come back when we talk about CW max. So basically, after the upper limit, you stop. After that, you throw away that data, tell the upper layer, fail, and move on. Okay, so you don't do it for an infinity, because if you do for an infinity, TCP will time out. So you don't want to worry about that. So you try it for a little bit, and that time is specified. It's coming up. Yeah, question.
Yeah, for retransmission, do we need to do those diffs and backups and things, or just after we understand that the packet failed, we just do the RTS, CTS, data, and ACK, or we just need to
No. You have to do everything. So basically, the question, you cannot just run the RTS right after your ACK not received.
Mm-hmm.
You have to just follow everything else. You go and sense the diffs and this and that, whatever we said, you have to follow those rules. Okay? Those rules are in addition to all this. All right, next slide. Will the data remain? Yes, the data will remain, is buffered until ACKed. When it is ACKed, then we throw it away. Nav is set to the duration of the message in the RTS, correct? Yes. So whatever you say, I want to send, then everybody else, when they see clear to send, then they will say, okay, all right, now this guy is going to be busy, so let me just be asleep for that time. All right, they shut off their circuit, and then the timer is the only thing that goes on, wakes them up, alarm wakes up, and then they say, okay, all right, let me see what is happening now. Okay, so they sleep. So yes. Okay. Is RTS in plain text? And this is a security question. The answer is yes. It goes in clear. The answer is RTS in clear text? Yes. Everybody hears it. Everybody hears it. Even your enemies hear it. Okay. All right. Next. PIFs uses PCF and DIFs uses GCF. What about CIFs? It's just the opposite around. PCF uses PIFs, DCF uses DIFs, and who uses CIFs? Okay, so PIFs is for PCF, DIFs is for DCF, and CIFs is for non-data traffic such as RTS, CTS, and ACKs. So if you go back to that diagram, this is CIFs. Sorry, this gap is CIFs. This gap is CIFs. So this gap is CIFs. So basically, the CIFs is used between control traffic, between whatever the previous thing is and your control traffic that is required. That is a must. That goes first. Okay. All right. Next, how does the coordinator select a station to transmit during polling? So here is the thing. I think I changed these 2 sentences just to clarify so that it is clear. Previously it says point coordinator, something I don't remember what it said, but now it says point coordinator reserves the time for stations to transmit. Okay, so this is a clarification here. The coordinator sends a beacon frame, and then it sends a polling frame to allow the stations to request contention-free access. So in the polling frame, I think this is a question of the polling frame. How does the coordinator select a station to transmit during the polling frame? So there is a small frame here during which people can transmit. All right. But here is the thing, though, even though the polling frame is sent and it is basically empty, that is an empty slot. So there are 5 slots which are empty, but they are really available only by contention. And this is something because it is in the contention free period, it is said here. But really, polling frame is where you go and say, hey, I need a PCF access for this much duration each second. Okay, your requests are made in that polling frame, and the other station will make a request too. And if 2 stations make at the same slot, then they will collide. Okay, so there is a polling frame, and that frame is mostly for requesting. And then when the station hears it, then they grant you probably in the beacon or in the polling frame. So all these details are in the details of the beacon and the polling frame. And they can vary from protocol to protocol. Okay, and my memory is actually more from WiMAX than from Wi-Fi. But basically, all this requesting is done here, and some of it is by contention. So those slots for polling frame come by contention. Okay, and if you get your access, all right, next time you request again, you say, well, I need that PCF access, please. Okay, and that PCF access is for, is repeating, basically how long you want to repeat, how often you want to repeat, for how long. So polling frame is set of empty time slots during which the stations compete by a random access to request PCF access. What does a point coordination function look like? PCF, what does a PCF look like? PCF access is periodic access like video. I mean, nobody watches a video for 1 microsecond or 30 microseconds or 30 milliseconds. They watch it for an hour, and the frames come every 30 milliseconds if you have 30 frames per second. Nowadays, we have 60 frames per second video, and we have 120 frames per second video. So we watch a lot of frames in every second, right? And so all that periodic access, every so many microsecond or millisecond, you need the access on wireless that comes by PCF. Yeah.
So I had 2 questions on a slide 5 and 12 that are not in the slides. Yeah.
Okay.
For slide 12, points. The second point says that if the medium is busy, transmitter backs off. So does it listen to nav or does it back off?
Listen before you talk. If the random is busy, transmitter backs off for a random period. Yeah. So what is the question?
If the medium is busy, the station should set its nav to the duration of the frame. So either
duration of the frame. You don't know the duration of the frame. You just woke up and you just saw that the medium is busy. What do? You don't know RDS, CDS, you didn't hear. If you heard RDS and CDS, you're already sleeping, man. You won't come back here.
So if it didn't hear that, just draw a random number and go, and after that random number expires, return and sense the channel. Correct?
Right. Is that the only question on 12?
Yes, and for slide number 5, I have another question. So here 802.1 QAU, the last point. The base standard is 1Q is the base standard.
Yeah, 1Q is the base. Whatever is the caps is base standard. AB is the base standard. Mm-hmm. So in this case, AB is a base standard.
Okay, thank you.
It can be more than one letter. In this case, Q is the base standard, AU is the extension. Good question. Now, I wanted to continue on your slide on 12. So basically, that was related to this thing here, right? There are many questions here. I think we didn't cover this yet. Okay, so let me cover these. Let's see, did we skip anything? The first question, we covered this part. No, we didn't cover that part. We covered this slide. We were on this one when you asked. Okay, so this question. Is the beacon part of the contention-free period? Or does it come before it? is the beacon come before the contention-free period? I was kind of divided in my mind, and maybe I will change this line to here, PCF access, but I didn't do today. But anyway, so here you think, this period is contention-free period, means basically it is pre-allocated. Everybody knows when they can do what, right? So there is no beginning and end. We don't say, okay, for the next 10 seconds is contention-free. No. We just, everybody knows that they can transmit for this time and this time and this time, whatever time, that is contention-free. And all we do is we give out the super frame duration. So we say it is every 10 milliseconds, I will send a super frame. And then Mr. 1, you can transmit up to this time here for PCF. Okay. And so Mr. 1 will transmit there. Everybody else will do DCF access after that. So these times are basically, even though they are shown here, they're not declared like that. And so whether the contention-free period is here or not is moot, M-O-O-T, because beacon is not contested. Beacon starts from a super frame, right? It is already reserved, and the polling frame is reserved, and the PCF is reserved. Okay. Now the question is, what happens if somebody runs into beacon? For example, if you start here, and your frame goes over, well, if the frame goes over, the beacon will wait. Okay? So the overflow, you are not truncated in the middle, because if they truncate you, then everybody lost the time for nothing. So the overflow is allowed. If you have very long frame and you got the CTS for that, you said, hey, I want to send for 1 hour, and you got 1 hour, then you can overflow that super frame. The next super frame will start after your frame is over. And that frame will start with beacon. Okay. And a lot of this detail is actually in the reading list, which I don't know if anybody has read, because nobody asked any questions related to the reading list. So I'm surprised. Okay. But anyway, let's move on. What is the unit of numbers in this example? Slots. Basically 3 slots, 4 slots. How much is a slot depends upon the speed. Okay. So it's the slots. For the time being, it is slots. Now, what you have to do is you have to draw after each successful transmission, you do CW min. Okay. But if you have unsuccessful, then you draw a number between your previous CW1 plus and CW max. Okay. And so after each unsuccessful attempt, between 2 CW, which was your previous CW plus 1, to CW max. All right. So this is actually different than what I would say later on. So let me just think about that for a minute. So for example, your CW min is 3 and CW max is 127. First time you start with a number between 0 and 3. You said, okay, no. CW min is successful transmission. Congestion window, sorry, this is a congestion window, not the back off. Okay, so there are three things here. First of all, you have to draw a random number. Okay, and the random number range is increased every time. So if you did first time and you succeeded, then you are set. If you didn't succeed, then you increase the range. If you didn't succeed, you increase the range further. Why? Because the reason you're not succeeding is because there is too much crowd out there. More crowd there is, we need more range to resolve that collision. Okay, this was done in Ethernet and was very well explained in 473. But I mean, basically, this binary backup is a standard thing. Okay, you keep increasing your range. And this is the range. The range first is CW min, and then it becomes twice and twice and twice until you reach CW max. So I think I have an example in one of the question, an answer to one of the questions which will come. here. Okay, right here. If two SS draw the same back off, how is the conflict resolved? Isn't this a collision? Yeah, it is quite possible that both of us draw random number 1, and both of us will, back off for 1. When we back off, we send an RTS again after 1. Then we will collide. So both will sense the medium after their nav expires, but RTS will collide and CTS will not be received. So now this is an unsuccessful attempt. So next time you draw not between 0 and 3, you draw 0 and 7. That is what that 2CW plus 1 was. 2CW plus 1. Your CW was 3, your range was 3. Now 2 times 3 is 6 plus 1, 7. Okay? And now 7 is fine. You don't have to do because your max is very high still. So you draw a random number between 2 and 7. So how is the CW min used? So how is CW min used, right? The first back off is between 0 and CW min. It is doubled on every retry. And the last back off is a CW max. After that, you throw away. So easy. For example, you started the CW min at 15. You will go from 0 to 15. Next time, you will go from 0 to 31. Next time, you will go from 0 to 63. Next time, you will go from 0 to 127. Next time, you will go 255, 5 to 11, and 1023. After that, sorry, the time is bad. Okay, there are just too many people. You better go to sleep. Throw away that packet. So these many retries are allowed. All right. There was an error that I discovered as a result of this, which was that I said CW min is 5. It cannot be 5. It has to be 3. Zibo, are you on? Zibo has left. Okay.
I'm recording, Professor.
Yeah, right.
I'm taking the notes.
I have to put it down here. See the slide number 519. So basically, it should be 3, power of 2 minus 1. Okay. And so that is how it goes. It goes, the range is increased and you draw a random number between those. Next. All right, I think this is the end. Now we'll go to, I have 12 minutes for slide number for module 6, which may be short. So I will run fast through 6. Let me see, 6 right here. And we start from 10, we go almost every slide after that. So let's go to 10. Okay, so 10, is MPDU equal to PSDU? The answer is yes. Why? Because MPDU goes this way, but how does it get there? It has to go downwards and come up. Okay. To go downward, this MPDU will be sent to the physical layer and it will be called PSDU. Okay. So it is equal. In some cases, it doesn't become equal because PPDU goes directly, it doesn't go, it goes to PMD, but it goes out, the bits go out. So basically they're shown going horizontally, but the reason they are dashed is because they cannot really fly in the air, they have to come down. And so they go to the next layer. And they become the service data unit for the next layer. Next question. Why is the coding rate here 2/3? The coding is right here, block coder. It takes 4 bits and makes 6 bits out of them. So your coding rate is 4 by 6. 4 by 6 is 2/3. You take 4 bits and add 2 more bits, that's like 2/3. Okay. Next, what is the relationship between DSS, CDMA, CCK, and QPSK? Some of these are modulations. So QPSK is a modulation, CCK is a modulation, and these are access methods. CDMA is for access method. Same confusion would be in OFDMA and OFDM. How do you access, right? And DSS, this is also basically spectrum access method, right? This is access method. Now, CDMA is one type of DSS. All right. So basically it is subset. So both are access methods, and there is many ways to do DSS. CDMA is one of them. Okay, now we can go back to spread spectrum. I think that was in very early module. So we cannot go there, but that is basically it. You can go back where CDMA was explained. Then you can see that CDMA and they both are spread spectrum techniques. And they both spread the spectrum. CDMA is one of them. So here I had 5.4 gigahertz band. And so this question was, is it 5.4 gigahertz or 5.8 gigahertz band? So actually, both answers are right. Three answers: 5 gigahertz band, 5.4 gigahertz band, 5.8 gigahertz band. You can write anything here. This was expensive. All these numbers were expensive at the time when this standard was done. So they didn't do it. And when they came to do it, some bands were available at one place, some were available at other place, some were not available at other place. So remember, when we said 20 channels at 5 gigahertz band, there were 12 which were contiguous in 5.4. There were 8 which were in 5.8. All right. So there is a gap in between 5.4 and 5.8. And the whole thing is called 5 gigahertz band. Okay. So I just put 5 gigahertz band so that there's no confusion about 5.4, 5.8. At that time, everything was expensive. Later on, these two bands came in and something in between is not used. But basically, some countries may not even have some pieces of it. Some countries may not have 5.8. All right. But all that detail is now lost because I checked Wikipedia, and Wikipedia says only 5.8 gigahertz for A, which is not correct. But I didn't want to fight Wikipedia. But basically, it is 5 gigahertz band. Okay. So I just fixed it here, 5 gigahertz band rather than 5.4. I had put 5.4, but 5 gigahertz band covers all possibilities. HCF. SCF has two components, and I had here PCF and EDCF, PCF and DCF, whatever, right? And the question was basically hybrid polling and EDCF. Hybrid polling was here, right? Yeah. So why did you substitute PCF with HCF in the figure? So here there's a PCF, there's SCF. I changed the figure just to be clear about all this because there are two parts. One is called controlled access, which is basically, it is not, basically it is contention free, but it is controlled, means that it is pre-reserved. It's a reserved compartment. You can travel into that only if you have reserved it before. That's why it is contention free. You don't have to fight for a seat. If you go in a general compartment, you have to find a seat, fight for a seat. Right? So this, we can call it PCF, we can call it SCF, we can call it CAP. CAP is the right word. So I put the word CAP here and I put the word CAP here. CAP is controlled access phase.
Professor?
Yeah, 1 minute. Let me finish this. That means contention-free access and hybrid polling. Okay, so that will include the polling that we talked about and contention-free access. Whoever is getting the PCF, they will be here. Yeah, question. Now we have to move fast. We have 6 minutes.
Yes, sure. We had this in homework 6A. So both answers are accepted? HCF
Okay, we will accept both answers later on. We can discuss that, okay? And we will accept both answers if this was confusion because of this. The slide has been corrected to CAP. CAP is controlled access. So, basically that includes PCF as well, right? So what is the difference between the classes of service and priority? Priorities are ordered. Ordered means that you can say 1, 2, 3. 1 is better than 2, 2 is better than 3. There is an order to them. In mathematics, they teach you ordered numbers, ordered sets. Things are ordered, okay? And classes of service are unordered. That means you cannot say one is better than the second. So I gave a very clear example of classes is black and white. Black is not lower than white, or white is not lower than black. There are two classes, period, right? But if you go to a train and you take first class and the coach class, they are ordered. First class people can probably not go into coach, and coach cannot. Well, first class people will go first anyway in the plane, regardless. And the coach class will go only when the time is available after the first. So they are ordered. So that is priority. Priority is an ordered set, and classes of service are unordered. Each queue gets 4 or 5 different parameters, question mark, answer is yes. These parameters are all different. Next, how is TXOP determined? Determined by the administrator program. You can go into your system and say, well, I want TXOP of this much, but nobody touches it. So generally it comes from the manufacturer. And if the manufacturer doesn't touch it, it comes from the standard. So there are recommended values in the standard. The manufacturers just don't bother. They just take the standard recommended value. The administrators don't bother. They just take the manufacturer value and the life goes on. Okay. TXOP is determined by the administrator. Next. So the ECCB FEC in point 9. ECC. Right. Should it be forward error correction or error correction coding? Both are same, by the way. ECC is FEC. Both are equivalent, but for 2 different communities. Storage people will never call it FEC because they don't forward anything. They just do ECC. If you buy a memory, it comes with ECC. The network people don't store anything. We just forward things. So we call it FEC. Okay, but they're exactly the same thing. Okay, they add an extra bit, we add an extra bit. We use the same formula. So FEC and ECC are same, but they are used by different communities in networking. We say FEC, they say ECC, and is used to randomize before the ECC coding. So now, wherever that picture was for ECC coding, I think that was probably in the memory or somewhere else. So that is a confusing place. Okay, you can call it ECC or FEC, but they are same. Can you please review the homework solution? Yes. How MPDU relates to file layer? Isn't PDU provided horizontally? Yes. So this is the same picture. PDU goes down, MPDU goes down, it becomes PSDU. So MPDU relates to file layer. MPDU is the service unit for the file layer. Okay, next. How can we calculate the usable bandwidth if we have number of carriers and guard interval length in second? If somebody gave me 114 carriers and they said the guard interval is so much, can we cover it? Well, actually, we might cover it in a later module. Okay, I remember somewhere in this whole course, we have these things done. This will be OFDMA will be with us throughout the course, throughout this course, including all the way up to 5G. So there are many standards on the way that we use OFDMA, and somewhere we will calculate it, but there are more numbers than just 2 numbers. You will need some more information. So if it is not covered so far, we will cover later module. Next. In the previous student question, it said it's lot 1. So this was an incorrect answer here. I corrected the answer. The picture is correct. So as said in the picture, the answer now says the same thing. 2 people said that, error corrected. Second, how many RTSs are used in each of the 3 cases? How many RTS? Each PDU needs a 4-way handshake. So there is an RTS. There are 6 RTS. Here, this is a PDU. So there are 3 RTS. This is 1 PDU, so there is 1 RTS. Each PDU starts with 4-way handshake. Okay, so that's how this is 6, 3, and 1. Now let's go back. Go. Okay, how did we get 96.3 megabits for 1 string? We just gave it to you. Assume that 96.3 megabits for 1 string. Period. Okay, and then you calculate for this one. So you multiply that and you get this. So this is given here. At some point, we will explain how to calculate using whatever.
Professor, I found it.
Yeah. Your question?
In the reference, there is a table for that.
Yeah, right. There's a table for that. So basically, the people have calculated it in that table, and at some point in your career, you would be able to prepare that table yourself, and we haven't gotten there yet. How do smart antennas form multiple? Now it is 2:20, so this time is overflow. I'm going to continue until the beacon because, sorry, I knew that today this will happen. It took me 6 hours to write all these answers. Mu MIMO, beyond this course, we can't answer that question. Next. How do stations know if the TV channels are available? There's a database. There are national databases. Next. Okay, I think that's the end. All right, now if you wanted to see the answer to homework 6A, stay around. Otherwise, here's what I generally tell my TAs, to put the correct answer or your incorrect answer. And the same thing will be done in the exam. If you haven't answered a question, you will not get the... Yeah.
So my question is that according to the definition of BSS, these two stations are in two different BSS. So one of
No, these two stations mean they are... Okay, let me just say one more thing. They are not in two different SSIDs.
BSSI, they are not.
They are same SSID.
So could you bring up a slide 22?
Slide 22.
Yeah. So the definition is a set of stations associated with one access point.
That is basic service set. See, the SSID belongs to ESS. Where is SSID here? So here there are two access. So the picture is not shown here, but this is one extended service set, one SSID.
This is one extended service set, and this is one.
So, I mean, here I think, if you go walk through the WashU campus, Boostal encrypted is one SSID, which has hundreds of access points. You get it?
So they do belong to
Extended service set, huh?
Yeah, extended service set, but different basic service sets.
Yeah, you can be in different basic service set, yes.
Okay.
Yeah. So, for example, this station is in medical school, or, maybe one part of the campus very far away from this access point. It cannot reach there, but can reach here. So you go to your room's access point, and that's it.
Okay, thank you.
Okay, any other question? Any other solutions that you need to see? Anybody who is left? Like right now, this is basically all being recorded and will be put. Except I think I will not put the solutions. I will cut out the solutions from the recording. I should have mentioned that, because we do not put the solutions online. Okay. All right. We'll see you the next time. Sorry. Thank you for staying over.